Thank you very much. And our last speaker for the session is Venkat, and I just moved his slide by mistake, I think, or you move it. So Venkat, thank you very much.
Good. Thanks. This is joint work with Michael Jordan, and it's about some interesting issues that come up at the intersection of statistics and computer science. And it's motivated by problems of the following type. So imagine that you're trying to place some sort of an ad on the sidebar, of a Google search, right? You're a company trying to place some ad. What you get information about is through some website. What you get information about is, some user searches for some term or looks at a certain website. You have some hopefully private information about the user, and you place a bid in some sort of ad exchange that sits sort of at the back end of some of these websites, and then the best bid somehow wins, right? And you wish to make a decision about what you're willing to pay to be able to place such a bid. And the constraint in this problem is not one of data. You have a ton of data about users and about user profiles, but the constraint in this decision-making problem is really one of time. You need to make a decision in a very small amount of time, usually on the order of microseconds and milliseconds, right? And this is something that classical statistics, or classical thinking in statistics, has sort of been ill-equipped to deal with. The sort of traditional viewpoint in statistics is that data is the key bottleneck, the amount of data. What's the best possible inference that I can make given a certain amount of data? This is really what underlies minimax estimation in statistics, minimax analysis in statistics. And these sorts of best possible estimation procedures that achieve the smallest possible risk or the smallest possible error given a fixed amount of data do not really take computational considerations into account. So the viewpoint is that data is the key constraint or amount of data, and I don't really care about runtime, at least in this sort of classical viewpoint. But more recently, evidenced by these sorts of ad exchange problems, time has become the key bottleneck, and in many domains, including some of the ones that have been mentioned in talks last year too, data is the resource that's plentiful, and time is the key constraint, runtime. And you need to make decisions in a small amount of time. How do I get rid of this? X, I suppose? Uh-oh. Carl, help. I've never used a Mac, so thank you. It's okay. Oh, okay. The mouse on the side, I guess, right? Anyway, the idea is that you need, thanks so much. The idea is that you need to incorporate time constraints somehow in this sort of thinking, right? And so here's a simple thought experiment that maybe gets us going towards trying to incorporate time somehow in statistical estimation. So consider a typical inference scenario, and I'm thinking really here of parameter estimation, trying to estimate some unknown parameter from data. You're given n equals 5,000 samples, 5,000 data points, and you process these data points for an hour on your computer, and you achieve a risk or statistical error or statistical accuracy of 0.03. You're now given 500,000 data points. You run your computer for 20 days, and you get a much smaller risk, 0.0003. What if I now give you 500,000 data points, lots of data, but I'm actually happy with a risk of 0.03? I don't care about this dramatic improvement in risk for several reasons. This improvement in risk, or the original risk that I have, is pretty small already, so I don't care about such small improvements in risk. Statistical models are also approximations to reality. They aren't reality. And so I don't necessarily care about obtaining really fine accuracy estimates of underlying parameters. And so what should I do in a setting like this? If the data or IID are exchangeable somehow, I can certainly throw away all but 5,000 data points, run my computer for an hour, and get a risk of 0.03. So certainly the amount of runtime that you allocate to this task should not be more than an hour, right? If you're given 500,000 data points, and you're happy with a risk of 0.03. But is it possible that the extra data that you have can be viewed as a resource to reduce runtime? Can you possibly say that with 10,000 data points, I can run a different algorithm in half an hour rather than an hour and get to the same risk of 0.03? With 100,000 data points, I can run my computer for just 5 minutes and get to a risk of 0.03. Actually exploit more data, the enhanced inferential power in a data set, in a larger data set, to reduce runtime. And so the idea really is, can I exploit, I guess, more data for computational reasons? And this really gets to something at the heart of, I think, computer science and statistics, and hints at some tension in these fields. In statistics, like I mentioned, the classical trade-offs tend to be between amount of data on the one hand and statistical error on the other, with really no consideration for computation as a constraint. In numerical computation, in computer science, we think of iterative methods where we run our algorithm for more iterations, reduce the error, analyze how these trade-offs behave. But we don't view data as a resource the same way we view time as a resource, right? More time is a resource in computer science. More space is a resource in computer science. But more data is almost never viewed as a resource. We think of data as a burden that you need to deal with, rather than viewing it as a resource to reduce runtime. And so this talk is really aimed at this axis, trying to understand, or this 2D plane, trying to understand trade-offs between runtime and an amount of data. And the way we'll think about this is to take some inference problem, think about this abstractly for a couple of slides, and then we'll make things concrete. Consider an abstract inference problem where we fix the desired risk, where we say, I care only about a risk of 0.03, like in that thought experiment we had a couple of slides ago. So we'll fix the desired risk, or the desired accuracy, and then we'll view inference procedures as points in a 2D plot, where the number of samples is on one axis and the runtime is on the other. And points in this plot are procedures that require so many samples, so much runtime, and will get you to your desired risk. Okay? And you want to view plots like this, right? As you get more and more data, that runtime actually reduces. There are certain low bounds. Anytime you have a plot involving trade-offs, the first question you should ask is, what do the horizontal lines mean and what do vertical lines mean? So what do vertical lines mean here? What's the minimum amount of data that you need, no matter any constraints in computation, to achieve your fixed risk, your fixed desired risk? And this is the domain, like I mentioned, of minimax analysis in statistics. What's the smallest amount of data to achieve this fixed risk, independent of computational considerations? And this is relatively well understood in many domains. We have a good handle on this in a large class of statistical estimation problems. The other axis, I would argue, is relatively poorly understood, and these are computational lower bounds. And so this is the question of, given access to an unboundedly large data set, what's the smallest number of operations you need to perform? What are interesting informed lower bounds in computation to achieve your fixed risk? And computational lower bounds, even in combinatorial optimization problems, are hard. And certainly these sorts of problems are also hard. They're poorly understood, depending on the kind of computational model. I don't know if the Turing model is the most relevant one for these sorts of algorithms we tend to employ in statistical estimation. And so this is a big open space. But in any case, we'd like to see plots that look like this. So what are some basic things we could say, even just by looking at this and talking about this abstractly and informally? The one thing is that we need weaker algorithms for larger data sets. As you get a larger and larger data set, you need to be able to back off to simpler and simpler procedures in the following sense. You need to be able to process larger data sets more coarsely. You want to process each individual data point in a larger data set more coarsely, so that you reduce runtime on the one hand, hopefully, and aggregated over a larger data set, you still achieve the desired risk that you set out to achieve. And so you need some mechanism to be able to back off to simpler and simpler procedures when you're faced with larger and larger data sets. If I give you 1 trillion data points, and there is a computational cost associated to touching each data point, then at some point it's going to make sense to just throw away data. right? At least in a setting where the data samples are IID. And so that's what I mean when I sort of hint at a floor like that. That at some point, it's just going to make sense to throw away data. This depends, of course, on the space of algorithms you choose to employ, but you will hit these kinds of floors. And also, given the fact that computational lower bounds are hard to obtain, when I talk about trade-offs between runtime and number of samples, I'll be talking about trading off runtime upper bounds. So when you give me more data, I'll produce a different algorithm that has a smaller runtime upper bound. So the worst case running time has a smaller upper bound as you give me more and more data. So that's the sense in which I'll be talking about trade-offs. So to make things concrete, let's consider a very specific estimation problem, and then I'll talk about a very specific computational framework to obtain these sorts of trade-offs. And this was the simplest estimation problem that I could come up with to talk about these trade-offs in a concrete way. And this is just sequence denoising from statistics. So you have a signal x star from some set S in p-dimensional space. The set S is going to be known to us, but the specific point in X that's the signal is unknown. And the observation model is as follows. You have signal corrupted by additive Gaussian noise, and you observe n IID samples from this model. And you wish to be able to reconstruct X star from these n IID samples. So you know the signal set, but you don't know the specific signal in that signal set. Okay? And it's clear that the sample mean is a sufficient statistic, so you take the average. And a natural estimator that you might be able to write down is to project that sample mean onto S. Now, frequently, the kinds of signal sets that we care about tend to be quite complicated. They're highly nonlinear, non-convex. Think, for example, of some set of sparse vectors, some set of low-rank matrices, some other more complicated set of structured signals that in general is intractable to project onto. And so what's done in these sorts of settings is to consider convex programming-based estimators, where you project onto a convex set rather than your original signal set S. And in this talk, we'll consider convex sets that are supersets of your original signal set S. So some convex outer approximation to S. And this is exactly the philosophy employed in, writing down the L1 norm as a relaxation for the cardinality function, the nuclear trace norm as a relaxation for the rank of a matrix, and so on and so forth. And this idea of projection onto convex sets, or shrinkage onto convex sets, is a long, long history in statistics. And convex sets have been particularly of interest from the viewpoint of computational tractability. And in settings where the signal set lives in a very high dimensional space, so P is very large, there are many interesting surprises, especially involving concentration of measure, as a lot of us know. Okay. So this is the estimator of interest. What is the performance of this estimator? What is the statistical performance of employing a particular convex set that contains S inside of it? To be able to analyze this performance, we need two definitions, and these are the only two definitions in this talk. The first is what's called the cone of feasible directions. This is an idea from convex geometry. So if I have a convex set C, and I have a point X star inside C, the cone of feasible directions is the set of all directions from X star into C. So if you think of a set S like this is a set C that contains S inside of it. X star is an element of S, so it's an element of C. And the cone of feasible directions is just the set of all directions from X star into C. This is the first definition. The second definition is that of Gaussian complexity. This goes back a long way in machine learning. What we'll need is an extra square, so I have a parenthetical squared here. And I'll specifically be worried about the Gaussian complexity of a cone. So if I have a cone T, a convex cone, the Gaussian complexity of this cone is given by this quantity. It's closely related to some of the things Joel was talking about. Huh? Equal to? What is equal to?
Same quantity.
Oh, they are the same quantity, sure. Sure. same quantity. It is, you take all vectors in this cone, normalize them, and take the soup of a Gaussian random vector with guys in the cone. And you take the expectation with respect to a Gaussian random vector z. This is the same Gaussian that was the noise in our observation model. Okay? And this goes back a long, long way in statistics. Gaussian complexity, Rademacher complexity is another notion of complexity of sets. And we specifically care about these complexities in the context of cones. Okay, so the risk of this estimator, which is the risk of that estimator we had a few slides back, where we projected onto the convex set C, and we projected the sample average computed from n samples onto C, is given as follows. The mean squared error is sigma squared divided by n times the Gaussian complexity of this cone of feasible directions. So the more pointed this cone is, the smaller the Gaussian complexity. And the less pointed the cone is, the larger it is, the larger the Gaussian complexity. So one simple example is that if you had no constraint, or in other words, C was all of RP, the whole dimensional space, right? Then the Gaussian complexity of all of RP is P. And so you'd get sigma squared divided by n times P, which is just the mean squared error, or the risk of the sample average. And straightforward proof, you only consider the error in the feasible cone. That's really all you need to worry about in this. But here's the thing. Going back to the setup that we considered right at the beginning of the talk. If we care about obtaining a fixed risk, so I only care about obtaining an estimate of risk at most 1. What's the number of samples that I need? You can just rearrange the terms up here, and the number of samples that you need is sigma squared times this Gaussian complexity. But if you have so many samples, the estimator x hat sub n of C will be an estimator with risk at most 1. Right? And so what does this tell us? If you look at this term, it's monotonic in C. The larger C is, the larger the cone of feasible directions from X star into C, and consequently, the larger the Gaussian complexity. And that's given by this figure. So you have a complicated looking signal set S, you take one constraint set C, and you take another outer approximation of that C, which is C prime. These are both convex sets. And once you've enlarged C to C prime, the cone of feasible directions becomes larger, and the Gaussian complexity of this is smaller than the Gaussian complexity of that. And so this whole quantity is monotonic in C. So if I give you access to a very large number of data samples, so n is very large, what can you do? You can use as large a convex set as possible, as long as this Gaussian complexity times sigma squared is less than or equal to the number of samples that you have. And if projecting onto larger convex sets is easier computationally than projecting onto smaller convex sets, you've actually obtained a time data trade-off, right? So large n, you can use a very large convex set, or as large a convex set as possible, so that this times sigma squared is less than or equal to n. And if I can show you, as I will in the next few slides, that projecting onto larger convex sets can be easier than projecting on the smaller ones, then we've obtained a time data trade-off. Okay? And for this, we'll need to appeal to, and this makes the same point that I just made, that if I can use a larger C, and if projection onto a larger C is easy, then we obtain a weaker estimation algorithm, and hopefully we can obtain a time data trade-off. And for this, we'll have to appeal to some really beautiful ideas in the convex optimization literature that have been developed over the last 10 to 15 years. And this is a very active area of research in that literature. The idea that when your signal set S has some structure, and I'm just going to say within quotes, algebraic structure, then one can write down a family of outer convex approximations in this way. And this family of outer approximations has two very interesting properties. One is that it's ordered in terms of approximation quality, so these sets are nested inside each other. So it is genuinely a hierarchy of approximations. But these sets are also ordered by computational complexity, in the sense that projecting onto C1 is easier than projecting onto C2, is easier than projecting onto C3, and so on and so forth. It is in general not the case that projecting onto a larger convex set is easier than projecting onto a smaller one. But you can design very specific hierarchies of approximations so that that is indeed the case. So you can construct very specific hierarchies based on linear programming or semi-definite programming or what's called hyperbolic programming. There are a ton of very prominent folks who've worked in this area that have the property that you have not just a nested hierarchy in terms of approximation quality, but also a nested hierarchy in terms of computational complexity. So appealing to these ideas, we can indeed establish time-data trade-offs in the class of estimation problems that I talked about, right? And a central role, if you're interested, I can talk about this offline, is played by this notion of lift and project in convex optimization. I would like to contrast to a lot of interesting previous work that's been done in this area of time-data trade-offs in machine learning. It actually goes back a long way. There are folks even in the bioinformatics community who care about these problems. This is a reference to papers in that community. There are folks in theoretical CS who considered notions of computational sample complexity, which tried to get to some of these ideas. A lot of these were done in the domain of binary classifier learning as opposed to the denoising problems that I've been talking about. And what's interesting in those examples is that you need a lot of extra data to be able to back off to really simple procedures. So you need massive amounts of extra data to be able to dramatically reduce computational runtime. And we'll see in some of our examples at least, although not in all, that you just need a modest amount of extra data to be able to back off to really simple algorithms. And this is a surprise, at least in these denoising problems. There are other domains as well where folks have considered time-data trade-offs. But one, I think, as a general high-level principle, one difference, one point of distinction between our work and what was done in these previous works is that our work really emphasizes this notion of algorithm weakening, the idea that you need a mechanism to back off to simpler procedures in a very principled way so you can exploit larger data sets, the enhanced inferential strength in a larger data set to reduce computational runtime. And convex relaxation is a very principled and very general way to do this. And especially given the interest in using convex optimization-based procedures in learning and estimation, this, I think, is potentially very relevant. Okay, so let's get to some really, some concrete examples. One example is a signal set S that consists of the outer product of a vector of the following kind. So AA transpose, where A consists of plus minus ones. So the signal set is just outer product of these guys. And these are what are called cut matrices. It's of interest in spectral clustering, collaborative filtering, and a whole bunch of other domains. The best possible convex set that you could project onto is just the convex hull of S. And that's what's called the cut polytope in computer science and in combinatorial optimization. It's hard to project onto. This is why the max cut problem, or one of the reasons why the max cut problem is hard. Max cut is the problem of maximizing a linear functional over the set. And so projecting onto that set requires runtime that's super polynomial in P, the problem dimension. But if, in fact, you could project onto that set, you would require n equals C1 times square root of P samples to be able to obtain a RISC-1 estimate. So again, we care about obtaining estimates that have a fixed desired risk. And in this case, the desired risk is fixed to be 1. A simpler set that you could project onto, which is what the Gomans-Williamson relaxation that Amit Singh talked about yesterday, uses is what's called the elliptope, and projecting onto that set requires that sort of runtime with a constant factor more extra data. You could also make the observation that the signal set S consists of rank 1 matrices. So you could use a trace norm or nuclear norm-based relaxation. That requires even less runtime, but with a constant factor more data. Okay? A second example where the signal set S consists of all perfect matchings in the complete graph. This is of interest in network inference problems. A matching in a graph is a subset of the edges of that graph such that no node is incident in more than one edge. And a perfect matching in a graph is a subset of the edges of that graph so that every node is incident in exactly one edge. So it's like a pairing, a disjoint pairing of the edges in your graph. If you take the set of all perfect matchings in a complete graph, these sorts of sets show up in network inference problems, and also problems having to do with reaction networks in chemistry and other areas. In this case, projecting onto the tightest possible convex approximation, which again is the convex hull of S, actually requires runtime that's polynomial in P rather than super polynomial in P like we had in the previous case. But I think it's of interest to talk about reducing computational runtime from polynomial time to less polynomial time in big data problems. So again, the contrast, previously we had very large runtime to polynomial time. In this case, we have a large polynomial to a small polynomial, and these are both improvements that are of interest. And this improvement here is obtained by making the observation that all perfect matchings in the complete graph, if you look at the adjacency matrix, consist of the same number of ones and the same number of zeros. And you can exploit that to construct a different kind of convex relaxation onto which projection is very easy. And even here, the number of samples required to be able to use this really simple approximation is just a constant factor larger. Again, to obtain a risk one estimate. The last example is one where we'll actually see a non-constant increase in the number of data samples required. And it's one that's motivated by sparse PCA, problems involving gene interaction networks and others. There are a bunch of folks who've looked at this. This paper is a nice one to look at an example of this problem. And it's where the signal set S consists of adjacency matrices of graphs where you have a clique on a small number of nodes and nothing else on the rest of the nodes. Just a planted clique in a large graph. And planted clique is a well-studied problem in combinatorial optimization and in computer science. Again, projecting onto the best possible convex approximation requires super polynomial runtime. And if in fact you could do that, that's the number of samples you need for a risk one estimate. You can again make the observation that adjacency matrices of cliques, if you put ones in the diagonal, are rank one matrices. And so you could use a nucleonorm-based relaxation, which basically just involves an SVD. And so the runtime reduces to p to the 1.5, but now the number of samples, the data requirement to be able to use, to be able to obtain a risk one estimate goes from the 4th root of p to square root of p. Okay. And so there are some interesting questions that are suggested by these examples. At least in some of these examples, you don't need too much extra data to be able to back off to really simple algorithms. And this is in contrast to what's the case in computer science. These really weak approximations tend to have what computer scientists call bad approximation ratios. But they tend to have good properties if your objective is statistical inference, at least in terms of ratios of these Gaussian complexities. These ratios of Gaussian complexities can be quite nice, even if the so-called approximation ratio is quite bad. And so I think the sense in which we evaluate relaxations of convex sets needs to change if your objectives are statistical inference objectives rather than combinatorial ones. And so I talked about some challenges with massive data sets and talked about time data trade-offs and these sorts of problem domains, and talked about convex relaxation as an algorithm weakening mechanism. I think there are a bunch of interesting questions for future work, and I'm happy to talk about these offline. The paper that describes these ideas is on my website. Thank you.
Before we entertain a couple of questions, I want to thank all the speakers that made my life very easy. Great talk, all on time, so it's great performance. And if you look at the average seniority in this session, you will be even more proud of their performance. You know, actually, almost all very junior, almost junior and a half. So, a couple of questions before we go to the great poster section. Yeah, please.
Yeah.
So, in your trade-offs, you had discrete set of choices going from 1 to 9.
Mm-hmm.
Is there any way to make it more competitive?
Yes and no, in the sense that I was appealing to these hierarchies of convex relaxations in the optimization literature, and they are very discrete. And that's the reason why I showed just discrete ones. There are ways one can interpolate between these sorts of things. In terms of solving one of these projection problems, which is a convex problem, what you'd actually do is run an iterative convex optimization solver, right? So you could imagine trading off, sort of spanning the gap between this and this by constraining the number of iterations that you use. And that's one proposal that some have talked about. So there are ways to sort of span this, sort of get something in between. I think randomization may be an interesting one, just like we do in decision theory, right? Where we randomize between different decision rules. And so that may be something that's possibly of interest too.